about a very basic concept, and this concept is possibility of a nuclear reaction. So we will try to find when a nuclear reaction can happen. So let me write down in our basic nomenclature. So let us consider a nuclear reaction. So this is our projectile, right? This is the target, and B is your ejectile, and small b and capital B is your residual nucleus. Okay, fine. Now let us use the uncertainty principle, the first thing. So this time we are proceeding by the use of uncertainty principle. Using uncertainty principle, we have delta x into delta px is greater than equal to h cross by 2. Now we will be interested in minimum uncertainty. So for minimum uncertainty, we have delta x into delta px equal to h cross by 2. Fine. Suppose we want to decrease this delta x, then of course px will be increased. Now let us assume that delta x is of the order of 10 Fermi meter, the nuclear size. Fine. Then you can do this estimation yourself, that delta px is of the order of, you can check for yourself that you get these results. And you will get the value of approximately. Now again, if you do the conversions to MeV, then finally you will get the value to be approximately 10 MeV by C. Okay, so this means that, what does this mean? This means that delta px must be greater than equal to 10 MeV by C. Okay. Now, so this was from uncertainty principle. Let me again write this over here for completion. So we have used basically uncertainty principle, and finally we are getting delta px must be greater than equal to 10 MeV by C. Okay. Now the next thing that we will be doing is use diffraction theory. So now we will use diffraction theory. Now in diffraction, we know that a wave of wavelength lambda will be scattered by an object only if the dimension is of the order of lambda, right? This is the dimension of object, and this is of course the wavelength. So then only we can have scattering is possible, right? So this means that a projectile will see a target and undergo nuclear reaction. So projectile will see target and undergo nuclear reaction if your de Broglie wavelength of the projectile is of the order of the dimension of target, right? There is nothing wrong with it. Now we have already previously assumed the dimension of target to be of the order of 10 fermi-meter. So this means my de Broglie wavelength of projectile should be of the order of 10 fermi-meter. Again, we know lambda is equal to hp, and so from here we get p of projectile approximately. If you do the calculations yourself, you will see that you will get this value 124 MeV by C. I ask you to do this calculations yourself. Okay, so this time we are using the diffraction theory, and this is the result that we are getting. Now if this is number 2 and the previous result was number 1, okay, then from both of them we can say that if both these relations, we can say that
স্যার ওটা পি এর তলায় ওটা কি লিখেছেন?
আরেকবার বলো।
পি এর তলায় ওটা কি লিখেছেন?
So these results 1 and 2 are conformity with each other, and they say that the nuclear reaction will happen if we have momentum of projectile is of the order of 100 MeV by C. Okay, so I am doing a sort of, you can say, this relation basically covers both point A and point B. So this relation is in conformity with uncertainty principle and your diffraction theory. Fine. Now let us consider some examples. That is important actually. So the first example is, so write it down. So question is, can we use the following projectiles for nuclear reaction? Or you can say, can nuclear reaction be produced by following projectiles? So what are the projectiles? Number 1 is 1 keV protons. See, here I am not giving any information about target, just I am asking about projectile. Again 1 keV proton, next 1 MeV protons. Number 3, 1 MeV alpha particle, and then your 100 MeV alpha particle. Now what is given here is mass of proton approximately 1 AMU and mass of alpha approximately 4.004 AMU. This is given. So let's first start. Before starting, let us write down conversion, right? Now we already have mass of proton approximately 1 AMU, and we know how much is this, approximately 940 MeV by c square. Next, so if we know this, then mass of alpha is 4.0040 AMU. So this means this is equal to 940 MeV by c square, and this is your 3764 MeV by c square. Okay. Now let's start with the first problem. The first problem is how much? 1 kV protons. Right, so this means that T is equal to 1 kV. Now total energy is equal to T plus m0 c square. So this is 1 kV plus your 940 MeV, or this is equal to 940,001 MeV, right? Also we know that E square equal to P square C square plus the relativistic relation. Okay, so now if we use this relation, and from this information of T and E, if we put this, then you can check out for yourself that you get P of the order of 1.37 MeV by C. So this means that for the case of 1 kV proton, nuclear reaction cannot happen because this is not greater than equal to 100. Okay, fine. So what about the next one? Next one. So next is your 1 MeV protons, right? Well, you can check that here your P comes out to be 43 MeV by C, and so this is 2 for 3 case. Now now you see 43 is approximately 100 in a way, so you can say that there is possibility that nuclear reaction can happen. What about number 3? Number 3 we have again 1 MeV but alpha particles. Okay, now here if you do the calculation, you will find that P is of the order of 87 MeV by C square. Sorry, here also C square will happen. So again here also nuclear reaction can happen. And then number 4 we have 100 MeV alpha. In this case you can again check that P is of the order of 873 MeV by C square. Look at this number. So this is of course greater than your 100, right? So this means that here nuclear reaction can happen. Any questions till now? Now before I finish this part, it is important. Right. Yes, momentum. Of course. Right. There will be C. No C square. Right. Okay. Now before I complete, let me just add one very important point here. So this was the relation, right? Now you see this expression is valid mainly for neutral particles. Okay, so it gives the constant momentum carried by a projectile small a from infinity up to range of nuclear force. Right. Now what happens for the case of charged particle? In the case of charged particle, there is a Coulomb interaction. So Vc, this is present, which is 1 by 4 pi epsilon 0 qa and q capital A divided by r square. So this means that the total energy now becomes T plus Vc plus m0 c square. Now at r tending to infinity, when the projectile is much farther than the target, then your Vc tends to 0. In that case, Vc tends to 0 when r tends to infinity, but other cases Vc will become important. So this means that as we accelerate the projectile so that it has kinetic energy T, and as it approaches the target, since the total energy is fixed and Vc keeps on increasing, so this means that T decreases, and due to this decrease, you understand the thing what I am saying? What I am saying is that this E is fixed, right? Now as this projectile comes near the target A, what happens is that this Vc increases. So Vc keeps on increasing. Now this is fixed and this is also fixed, so this means that your kinetic energy will keep on decreasing, and due to this decrease in T, what will happen is that your momentum will decrease. So this means that at the range of nuclear force, if P is of the order of 100 MeV by C, then only nuclear reaction can happen. You can say